Ok, stiamo registrando. L'abbiamo fatto. Ok, so, vedete la slide a casa, giusto?
Sì, sì, sì.
Okay. So as you see from the title, we are now in the last module of the course that will be covered by today and tomorrow lessons. And today we will discuss about the phenomenon of neutrino oscillations. So let me start with an overview of the neutrino sources that we have that can be reached the Earth, that can be detected at Earth. So we have, so you see here different sources of neutrinos as a function of their energy. And in particular, so we can have neutrinos originating from the Big Bang, which are expected to be very low energy neutrinos. Then we have the solar neutrino, which are in the range of kiloelectron volt, tens of kiloelectron volt, okay? In some cases also up to 10 or 15 MeV. And you see within each of these triangles the main experiments that have been set to study these different neutrino sources. And then we have the terrestrial neutrinos, which are neutrinos produced in the mantle and in the Earth crust due to the beta decay of some heavy isotopes, which are in the underground. Then we have reactor neutrinos, so neutrinos that are produced in reactors for nuclear fission, that can be used also to make first fundamental science. Neutrinos from supernova explosions, and a very nice event was observed in 1987. So a supernova explosion in the galaxy was actually correlated with a bunch of neutrinos reaching the neutrino detectors on Earth. Then we have also accelerator neutrinos, so we can produce neutrino artificially through accelerators. So we accelerate protons, we hit proton in some whatever nuclear target. We produce pions, pions decay into muons, muons decay into neutrinos, for instance. This is one way. We can also have atmospheric neutrinos, which are now in a higher energy region, as you can see, which are neutrino produced as a secondary product of the interaction of the very high energetic cosmic rays on the atoms of our atmosphere. And then we have also so-called cosmic neutrinos, which come from very energetic and dramatic events that happen in the far universe, like active galactic nuclei, black holes, whatever. And these cover the very large energy region of this spectrum. Okay. So let me start with the solar neutrinos, and in particular, actually studying the so-called solar neutrino problem and how it was at the end solved and understood. So in the standard solar model, SSM, as you know, the sun produces energy via thermonuclear reactions that occur in its core, which is a region around 10% of the solar radius, but which concentrates roughly 1/3 of the total mass of the sun, where the temperature of the order of tens of millions of Kelvin. Now, as you also know, the most efficient thermonuclear reaction in the sun are those that enter the so-called proton-proton chain, which altogether provides 99% of the solar energy. So the chain is depicted here. So we start, for instance, from two protons, okay, in the plasma of the star, of the core of the star, and these undergo a weak interaction, okay, which at the end leads to the formation of a deuterium nucleus with emission of a positron and a neutrino, okay. So this is a very important source of solar neutrinos, in fact. Then the deuterium nucleus can interact with an additional proton to produce an helium-3 nucleus with emission of some photon. And then two of these helium-3 nucleus can interact to form an helium-4 nucleus plus two protons, okay? Each fusion reaction chain, okay, so overall for this chain here, releases about something like 26.7 MeV, okay, which are mostly carried by the photons which are emitted here. Now, what about these photons? These photons are produced in the core of the sun, but of course they, in order to reach the surface of the sun, and so to be emitted by the sun, they need some time because they undergo a very long series of processes of absorption and emission, absorption, emission. And as you can see here in this cartoon here, actually it takes something like 200,000 years for a photon produced in the core to reach the photosphere of the sun, because of this very complex absorption and emission process. Okay, the radius of the sun is something like 700,000 kilometers. And then once the light arrives to the photosphere, okay, it is then released by the sun, and then it goes everywhere. And in particular, the photosphere is indeed the outer layer of the sun with a temperature of only 6,000 Kelvin compared to the 15 million Kelvin inside the nucleus. But this is not, as you understand, the end of the story, because in future reaction, also a very large flux of electron neutrinos is produced in this, in particular in this very first stage of the proton-proton chain reaction. And neutrino, as you know, they interact extremely weakly with matter, only through the weak interaction. So they only take 2 seconds to reach the surface. Okay, they travel essentially at the speed of light. So it's 2 seconds compared to 200,000 years. You see the immense difference between the propagation through the sun plasma. And indeed, the amount of neutrino which is produced in the nuclear reaction in the sun is huge, it's really huge. And of course, only a very small fraction of those neutrinos reach the Earth and reach us, okay? And consider that every centimeter in the Earth's surface is crossed every second by 60 billion neutrinos, okay? So in this very moment, in 1 centimeter of my hand, 60 billion neutrinos are crossing me, okay? Quite impressive. Of course, we don't even notice this because the interaction with neutrino is extremely rare and extremely weak. Now, the dominant proton-proton reaction, yielding 90% of the total flux of solar neutrinos, produced low energy neutrinos, okay? So the energy, as you can see, is only a fraction of an MeV. The endpoint is of the order of 0.4 MeV. But the proton-proton chain is not the only reaction chain that occurs in the sun, okay? There are many others. So the proton-proton starts, as I was saying before, by this weak process. So the 2 protons produce a deuterium, and then we have here the first release of electron neutrinos. And then with a very large, high efficiency, so essentially 100%, the produced deuterium interact with the additional proton, which is available in the plasma, to create an helium-3. And then twice of this reaction produce 2 helium-3, and so at the end we follow this branch here with a very large probability, and at the end the 2 helium-3 produce an helium-4 plus 2 protons. So this is the path for the standard proton-proton chain, okay? Now, many other things can actually occur with less probability, of course, in the sun. So for instance, when we are now at this stage, the chain can also proceed in this direction, okay? So the helium-3 can also find some helium-4 in the plasma to create a beryllium-7, and the beryllium-7 then decays weakly into a lithium-7, producing another source of solar neutrinos, electron neutrinos, okay? Then the lithium can also catch a proton to produce 2 alpha particles, 2 helium nuclei, and this is the proton-proton 2, the Pro2 chain, okay? There could be other branches. For instance, in this case, for instance, can go this way. So the beryllium-7 can now catch a proton to obtain the boron, and the boron now decays weakly in the beta decay to an excited state of the beryllium. And again, we have another source of electron neutrinos, okay? These are the neutrinos from the boron. And then further, the beryllium can also at the end produce 2 helium-4 nuclei. And we have also other possibilities. This is the proton-proton 3 chain. We have also this proton-electron-proton reaction. Okay, you see we have 2 protons and electron in the initial state, and this is a source of neutrino, but now with the probability of only 2 per mil. Okay, so the flux for neutrinos from this chain is very small. This is actually even 1 per mil, smaller. And then we have this very, very low probability reaction, where one can get electron neutrino also from helium-3 plus proton in the Li4 and positive. Okay, and this is the HAP chain. So all this to say that okay, so the majority of the neutrino come from the proton-proton, of course. Okay, and there are low energy neutrino, as I said, up to 0.4 MeV in energy. The beryllium-7 neutrinos, so those produced in this part here of the chain, have energy of 0.86 MeV, so still low energy electron neutrino. And it is the second most relevant electron neutrino source in the Sun, which accounts for something like 8% of the total electron neutrino flux from the Sun. Then the PEP, so this guy here, accounts only for essentially the 2 per mil of the electron neutrino fluxes and produces electron neutrino with the energy of 1.4 MeV. And then if you look back to this proton-proton 3 chain, okay, here we have the contribution to the flux of the order of 1 per mil, but in this case, the electron neutrino which are produced from the boron are much more energetic, so they reach energy up to 15 MeV. Okay. And here you see essentially the fluxes of all these solar neutrino sources as a function of their energy. Okay, so the most prominent flux, of course, is the one from the proton-proton chain. Okay, the first that we discussed. Then we have this is a log scale. Okay, so consider any drop of this is 1 order of magnitude. Then we have the beryllium-7, which is the second most probable. And then we have the others decreasing. Okay, so for instance, the one from the boron, which are the most energetic, have a very, very small flux compared to the proton-proton. Now, people, of course, want to detect the neutrinos produced in the Sun, mainly to, in a sense, confirm the solar standard model that was proposed in the 60s, essentially, by John Bacall, because the solar standard model was a very sophisticated model which made precise prediction of the fluxes of electrons from all these reactions that we should observe here on the Earth. So the first solar neutrino experiment was performed in the late 60s by Ray Davis in the so-called Homestake mine in South Dakota in the United States. And the experiment consists in counting the number of argon isotopes produced in 600 tons of this compound of chlorine through this reaction, which is an inverse beta decay, okay, where the chlorine at the end produces indeed argon when interacting with electron neutrino. Okay, so this is essentially at the more elementary level, this is the inverse beta decay process. Now, the surprise at the time after this experiment was that essentially they found only essentially 1/3 of the expected flux of the solar electron neutrinos. Okay, so in other words, the standard solar model was predicting a certain flux, okay, very precisely, but the experiment revealed only 1/3 of that flux. And this was indeed the beginning of the so-called solar neutrino problem, which took 3 decades, actually 4 decades, to find a solution, 3 to 4. Now, of course, the experiment was repeated by others, and also with very different experimental setup and very different techniques. But nonetheless, in the following 30 years, okay, all these solar neutrino experiments found a significant deficit of the observed electron neutrino flux with respect to the prediction of the standard solar model. Okay, so there was a kind of mystery here. And among this experiment also, the Kamiokande and the Super Kamiokande experiment searched for electron neutrinos. These are, of course, in Japan, as we already mentioned long ago in the course. And they also found a significantly lower flux of electron neutrino than predicted by the standard solar model. Now, this experiment, we will also talk a bit more later, used ultra-pure water as a target material, so something like 5,000 tons in the case of Super Kamiokande. And this water was essentially the radiative means for the production of Cherenkov light, okay? When the neutrino essentially interacts weakly, producing a charged lepton, which produces a Cherenkov cone in the detector, okay? And since essentially the direction of the electron is pretty much the same of that of the incoming neutrino, tracing back, it was possible to indeed find that the neutrino was coming from the sun. So you can project back the space and find that the neutrino indeed comes from the sun. Fantastic. Now, so the question is, after 30 years of experiments, was the solar standard model wrong, or some solar electron neutrinos were disappearing in their way to Earth? And the final answer of this mystery, so this long-term mystery, indeed, the solar neutrino problem, was provided by the Subdurian neutrino experiment, SNO, which was performed in Canada. So SNO used 1,000 tons of heavy water, where heavy water is D2O, so where the hydrogen atom is substituted by a deuterium atom here. And the reason for this is it will be clear in a moment. Okay, so essentially the target was the deuterium, the target, and this experiment was sensitive mainly to the high energy electrons coming from the boron chain. Okay, which only accounts for a marginal flux, a marginal fraction of the total flux. So, why is so important to look at interaction with the deuterium? Okay, because in principle you can have both charged current and neutral current interaction with your neutrino with the deuterium. Okay, for the charged current, the neutrino, either electron, muon, or tau neutrino, interact with the deuterium nucleus. Okay, and at the end you obtain the corresponding charged electron. So the electron, the muon, the tau, and then you have two protons in the final state. The neutral current instead essentially is a breakup reaction. Okay, so the energy released by the neutrino when interacting with the deuterium nucleus, which is a loosely bound nucleus, with only 2.2 MeV of bound energy, is to break up the deuterium. Okay, so at the end you get indeed the same neutrino and the neutron and proton, which are the constituents of the neutrino. Okay, so what is now the important point here? So the crucial point is that while all three neutrino flavors, electron, muon, and tau, can contribute to the neutral current process. Okay, so you put X can be electron, muon, and tau. It turns out that only the electron neutrino, so the first family, can take part to the charged current interaction. And the reason is that to produce an electron, it is easy. You just need half an MeV. Okay, but to produce a muon, or even a tau lepton, you need a lot of energy in the center of mass. Okay, the tau is almost 2 GeV, and but the energy of our solar neutrino is very low. Okay, or less than a few MeV at most. So in practice, those two reactions cannot occur because they are below the energy threshold. Okay, and so at the end, the only two processes that can be studied with the deuterium target are, and with the low energy solar neutrinos, are the charged current electron neutrino deuterium into electron proton proton that you see here. So the electron neutrino converts into an electron, and then the W transforms the deuterium into two protons. Or, and this is only for the electron flavor, or the neutral current, which can be for any of the three flavors. Okay, where now essentially the deuterium nucleus is broken up into a proton and neutron. And the importance of this is that indeed the SNO had for the first time the possibility to disentangle the two things, because one process can only occur for electron neutrino, and the other process can occur for all types of neutrinos. And so SNO provides for the first time a way to separate the measurement of electron neutrino fluxes with the measurement of all the other neutrino fluxes. And this was at the end crucial for understanding what is going on. So by doing this way, SNO found that indeed the ratio between the flux of the electron neutrino with respect to the total flux of neutrinos, electron, muon, and tau, is of the order of indeed 1/3. Okay. And the total flux of neutrinos, so the denominator here, is perfectly consistent with the expectation of the solar standard model. Okay, so the solar standard model indeed works well, but something happened to the electron neutrinos. Okay, and in fact, this result indicates clearly that the electron neutrino might transform into a different neutrino flavor during their journey from the sun to the Earth. We can summarize the results from SNO in this plot here. So here we have in the x-axis the flux of the electron neutrino divided by the total fluxes predicted by the solar standard model, and in the other axis you have the joint flux of the muon and the tau neutrino, again divided by the total flux predicted by the standard model, solar standard model. Okay. So the vertical yellow band, okay, is the result from SNO based only on charged current analysis. In fact, you see here a value of 1/3. Okay, so this can only reveal electron neutrinos. The diagonal band instead is the result of SO from the neutral current analysis, which takes into account all three flavors. Okay, and then of course you can take the intersection of the two, and this is essentially the overall result. So indeed, what happened here is that the detected electron neutrino account for about 1/3 of the total flux expected by the solar standard model, and the joint muon and tau neutrino for the remaining 2/3. Okay. Now you can compare the global result, so fitting together the neutral current result and the charged current result. Okay. And your global results, which you see indicated by this ellipse here, which indicate a 68% confidence level, so essentially 1 sigma uncertainty, touches the line here, the solid line, which is the prediction from the solar standard model. Okay, so within 1 sigma, so perfectly consistent, the SNO results are consistent, confirming that the total flux from neutrinos coming from the sun is indeed consistent with the prediction of the standard model. And what is missing, so is a fraction of the electron neutrino, is because they, by sure, have to have changed flavor during the way from the sun to the Earth. Okay, so at the end, the solar neutrino problem could be solved without modifying, without touching the solar standard model, which was actually correct. And the solution is that the solar neutrino change their flavor during their way to Earth through a phenomenon that today we call the neutrino oscillation, that we will study today. È chiaro, ragazzi? Now, another very important solar neutrino experiment is Borexino, and I like to cite this because it is, of course, an Italian experiment. It was sitting in the Gran Sasso Underground Laboratories under the Gran Sasso Mountain, which was needed to shield, of course, the huge background from cosmic rays, because you want to work in this virtually free background environment if you want to look for such rare events. Okay. So differently from SNO, which was only looking to the high energy neutrinos from the boron 8 reaction, Borexino was able to touch essentially all possible neutrinos coming from all possible reactions in the sun. Okay. So was able to measure separately the neutrino fluxes for all the principal reactions and covering essentially the whole energy spectrum of solar neutrinos. Not only, in the second phase, Borexino was also dedicated for the study of the so-called geoneutrinos, as I was mentioning before, which are neutrinos emitted by the isotopes of uranium, thorium, and potassium, which are present in the mantle and the crust of our Earth. Okay? And a measurement of these geoneutrinos provides an estimate of the heat that is produced inside our Earth. Okay? Now, this is an overview of the Borexino detector. Okay, so the core of the detector is a spherical vessel of liquid scintillator material. So when a neutrino interacts with the material, it produces a charged electron, for instance, an electron, and the electron excites the molecules of this scintillator, and at the end, the light is released. And the light, the scintillator light, is detected by an array of photomultipliers which surrounded in the 4π the scintillator material, so the fiducial volume of the detector. You see also here a quite impressive picture of the inside the vessel. Then there was a buffer, and then outside there was water to stop particles produced from the radioactive decay of the surrounding in the cavern. Okay, and also there were muon PMTs that were looking at the external of the fiducial volume, just to make anti-coincidence with the background events coming from outside. And the strength point of the Borexino was its capacity to suppress the ambient radioactivity to an unprecedented level. So consider the radio purity of the material that were used to build the experiment were at the level of 1 part over 10 to the 19. Quite impressive. Of course, if your detector material contains radioactive impurities, then you are faking your result, right? So it has to be most pure as possible. And another solid evidence of the neutrino oscillation came also from the atmospheric neutrinos. Okay, so atmospheric neutrinos essentially are produced, as I was mentioning before, as a byproduct of the collision of a very high energy cosmic ray with the atoms of our atmosphere. Okay. And differently from the solar neutrino, the atmospheric neutrino, first of all, have much higher energies, and also they can arrive from any direction. So the solar neutrino come from the sun, but the atmosphere is everywhere around us, so atmospheric neutrino can reach us from any possible direction. Now, let's consider, for instance, the chain that you see here. So we have a very high energy cosmic ray, which can be a proton or a light nucleus, or up to the iron nucleus that interact with our atmosphere. Then in the collision, of course, a lot of energy is released, which is converted in the production of new particles, which at the end produce a shower that goes down into, through the atmosphere up to the Earth's surface. In this shower, we have a lot of pions. Okay, the pions, as you know, decay weakly into muon and muon neutrino, and the muon at the end also decays into electron with the production of electron neutrino and muon neutrinos. Okay, so this is the basic decay chain, and this can be initiated either by a pi plus or a pi minus. Okay, so for a pi plus, we have a mu plus and a muon neutrino, and then the mu plus decays into a positron, electron neutrino, and muon antineutrino, and opposite for the pi minus. But now you can count your relative amount of neutrinos, and you find here that indeed you have 4 muon neutrinos or antineutrinos and only 2 electron neutrinos or antineutrinos. Okay, so if you do expect these to be what is really happening, you expect the ratio between the muons neutrino and antineutrino with respect to the electron neutrino antineutrino should be 2, exactly 2. Now, this is indeed what is measured. So the ratio is indeed 2, but only when considering neutrino impinging the detector from the top. So if I go back to this slide here, if you consider cosmic rays in this direction and the neutrino reaching our underground detector from the top to the bottom, then indeed this ratio is 2. However, when now considering electron neutrino coming from the bottom, okay, so they do a shower in the atmosphere and then they cross essentially the entire thickness of our Earth, then it turns out that this ratio is 1. So something is happening when the neutrinos are crossing our Earth through our detector. Okay? And in fact, a ratio of 1, of course, indicates that there is a clear deficit of muon neutrinos. We will come back to this in a moment. But why? Okay, so why should the muon neutrinos decay in the case they come from the bottom, so they have to cross the entire Earth? What is happening there? What is the difference with respect to the bottom and top scenarios? Okay. So the question is the following: while all neutrino flavors interact equally with matter through the neutral current processes, okay, the charged current interaction with matter are flavor dependent. Why? Because the ordinary matter, also including the plasma in the stars, of course, provide a huge amount of electrons, but essentially no muons and no tauons, no tau electrons. So there is an obvious asymmetry in the charged electrons which are present in ordinary matter. We have electrons, whatever you want, but we don't have essentially muons and tauons. So we can also look this into more detail from the Feynman diagrams. Okay. So the first one is the neutral current process. So our matter is an electron. It can be atomic electron or electrons in the plasma of the sun or whatever star you want. Okay. And in this case, whatever neutrino family you consider, okay, the process is equivalent and the probability is equivalent. It is just a neutrino electron scattering mediated by a neutral current. However, if you now consider the process with the exchange of AWs, okay, and you only have electrons, okay, matter, then this can only involve electron neutrino. You can never have here a muon or a tau neutrino. Okay? A tau neutrino or a muon neutrino cannot interact with an electron through the exchange of a W. The W only provides you changing within the same family of electrons, as you know. So there is a clear difference between the neutral current process and the charged current process. This one is completely democratic, this one is not. Okay, this one works only for electron neutrinos. And this different contribution to the scattering amplitudes, in a sense, corresponds to a different refraction index, if you like, of the electron neutrino compared to the muon neutrino and the tau neutrino. So in other words, matter appear more opaque to the electron neutrino than to the other. Okay, because the electron neutrino have this additional way to interact with matter that the other neutrino have not. And as a result, the neutrino oscillation phenomenon is affected by the passage through the matter. Okay, and this is indeed the reason for this atmospheric neutrino coming from the bottom. So in fact, in particular, it can be shown that the neutrino oscillation probability is strongly enhanced whenever neutrino travels through matter because of this asymmetry here. Okay, for instance, through the sun or through the earth or through whatever body you want. Okay, as compared to the case where the neutrino are propagating in the vacuum. Okay, so the presence of matter impacts significantly the probability for the neutrino oscillation. In other words, this is called the MSW effect from the initials of the three theoretical physicists that for the first time predicted this mechanism. So back now to our atmospheric neutrinos. Okay, so we have these two possibilities. We have an underground detector close to the surface in the top part of the Earth, and we have more neutrinos either arriving from the top or from the bottom. In the first case, they only travel few tens of kilometers in the air and possibly few hundreds of meters in underground, so in the rock. In the other case, they cross the same atmosphere, but now something like 13,000 kilometers, which is the diameter of the Earth. So there is a big, big difference, okay, in the path through matter of neutrino coming from the top or coming from the bottom. And in fact, when looking now only at neutrino coming from the bottom, in the detector, indeed the ratio is 1. It's not anymore 2, but it is 1. This means that now there is not any more access for the muon neutrino compared to the electron neutrino, and so part of the muon neutrino have disappeared in the process. And how can we understand this disappearance? Are they absorbed? Well, one can make calculations. Of course, the cross-section for interaction of the muon neutrino is extremely low. Okay, so the probability that the muon neutrino disappear because we are absorbed in matter is extremely low, and cannot explain the change of the ratio from 2 to 1. Okay, so the only way to explain this is not that the muon neutrino are absorbed, but instead that they have oscillated in a different type of neutrino. Okay. For instance, if in this case, if they oscillate from muon neutrino to tau neutrino, and the detector is not optimized for detecting tau neutrino, you find something missing. Okay, and this explains why we get 1 instead of 2. Chiaro? Now, let's now be a bit more quantitative and in the discussion of the neutrino oscillation phenomenon. Okay, so the phenomenon of a neutrino oscillation, so the oscillation between different neutrino flavors, so electron to muon, muon to tau, etc., as we will see, requires a non-zero neutrino mass. And this is a very big problem for the standard model of particle physics, because in the standard model, the neutrinos are massless, in the sense that they cannot receive mass by interacting with the Higgs field. They actually have no interaction at all with the Higgs field. Okay, and so for the standard model, they have to be massless. But if they are massless, they cannot oscillate. We know that they oscillate, so we know that they have to have mass, and so we know that something is missing in the standard model. So how can we understand this neutrino oscillation phenomenon? Okay, so this oscillation arises from the fact that similarly to quarks, as we studied a few weeks ago, the weak eigenstate of the neutrinos, so electron, muon, and neutrino, do not coincide with the mass eigenstate of the neutrinos, which we will call μ1, μ2, and μ3. Okay? These are the eigenstate of the free particle electrons. Okay? So the two do not coincide. And as a consequence, any neutrino weak eigenstate, for instance, the electron neutrino, okay, is given by a superposition of the three possible mass eigenstates. It's a combination of the three possible mass eigenstates. Okay. Just to make things simple, if you consider only two neutrino flavors, okay, we have the μ1 and μ2, which are the two mass eigenstates, and then the physical, so the not physical, but the weak eigenstate neutrinos, the electron and the muon, are mixtures, different mixtures of these two mass eigenstates. Okay, and this, of course, has to be extended for the case of three neutrinos and three mass eigenstates. So what happened physically? it happens that a weak eigenstate neutrino, for instance, an electron neutrino, which is produced in a decay of the W, for instance, okay, it is produced as a flavor neutrino, but it propagates in space as a combination of the three mass eigenstates. Until when? Until it interacts with some medium, and so its wave function collapses into the corresponding charged electron, so electron in this case. Okay, so you create as a flavor neutrino from some weak process, but the flavor neutrino propagates in space as a combination of three mass eigenstates until it interacts, and at that point the wave function collapses into the corresponding charged electron. Okay. Now, in particular, if the masses of the three mass eigenstates are not the same, and not all vanishing in particular, then phase difference arises between the different components of the wave function, and this is why the neutrino do oscillate. You can see this in this very simplified picture. So suppose you start with a Mu neutrino, okay? And the Mu neutrino we can imagine as a superposition of two mass eigenstates, E1 and E2. So in this very moment, the two mass neutrino eigenstates are in phase, okay? And this is the Mu neutrino. Then they start to oscillate as soon as they propagate in space with different frequencies, okay? And so at a certain point, they are not anymore in phase, okay? And so our neutrino is not anymore a pure Mu neutrino, but it is a combination of different neutrino flavors. Then there is a point where the two components have opposite phase, and this is the case where now our Mu neutrino has oscillated into an electron neutrino. Then this object continues to propagate, so the oscillation continues, until again the two mass neutrinos are in phase. And this is again where the Mu neutrino appears purely, okay? And so on and so forth, okay? So this is the way neutrino oscillation works. Now, as I was already shown here, the oscillation phenomenon can be easily shown for the case of two neutrinos. So let's for the moment focus only on the electron and the Mu neutrino, and then we will generalize the formalism for the case of three neutrinos. So as we said, the neutrino propagates in space in terms of mass eigenstates, okay? And so we can describe the wave function of these mass eigenstates as plane waves, okay, in the usual way. So they propagate in space as plane waves. Now, in perfect analogy with the Cabibbo quark mixing, okay, we have exactly the same notation here, okay? So the weak eigenstate, electron and Mu neutrino, are related to the two mass eigenstates through a 2x2 unitary rotation matrix, okay? So in a sense, the weak eigenstate, the electron neutrino and the Mu neutrino, are rotated states of the mass eigenstates through this rotation matrix. And so we can compute now this matrix vector product, and we find that the electron neutrino is given by this specific combination of mu1 and E2, and the Mu neutrino is given by this other specific combination of mu1 and E2. Okay? And then, of course, one can also invert the matrix, and one can obtain now the expression of the two mass eigenstates as a function of the two level eigenstates. Okay. Now let's develop the formalism on the blackboard. For the simple case of two flavors. Okay, so we suppose that at the time t equals 0, and electron neutrino is produced by some weak process, okay? To be the decay of a W, whatever you do. Okay? So the wave function at time 0 will be that of a pure electron neutrino. And this we can expand now through the rotation matrix in terms of the two mass eigenstates. So this is cosine theta u1 plus sin theta u2. Now, this is at time 0. Okay, at a time greater than 0, of course, these two objects, 1 and 2, are propagating in space as plane waves. Okay, so for the time t, let's say space-time coordinate x and t, these is not anymore a pure electron neutrino, of course, okay? And we can now substitute here the cosine theta, and then we have our wave I21x plus sine theta into minus I x. Now, suppose that the neutrino at a certain point interacts. So after traveling a distance x equal L and the time. So it is generated by some weak process at time 0, then self-propagates as a combination of mass eigenstates, and then at a certain time, capital T, after traveling the distance capital L, interacts with matter. Okay? So what is now the wave function at this time and position? So this is cos theta, V1, where T the minus I by 1 plus sin theta into e to the minus I by 2, where phi I is just the argument of the plane wave. Okay? So it is in general p I x, and so this specific space-time point is e I t minus p I. Now, let's consider now the inverted rotation matrix. So we can now express the mu1 and mu2 in terms of the flower eigenstates. So as we've seen in the slide, mu1 is the cosine theta mu2 minus the sine theta mu, and mu2 is the sine theta mu electron plus the cosine theta mu. This is from the inverted rotation matrix. And so we can now substitute this expression here and there. Okay. So what we get is cosine theta that multiplies this object here. So it is cos theta in B minus sin theta mu times e to the minus I1 plus sin theta that multiplies this other expression, sin theta mu plus cos theta mu times e to the minus I2. Now, let's collect all the terms with the electron neutrino. So here we have the exponential first, so e to the minus I e1, and then we have the cosine square of theta, plus e to the minus I by 2, and then we have now the sine square of theta. And we do the same for the other piece. So this is going to be e to the minus I e1 minus e to the minus I by 2 cos theta sin theta mu. Let me now put outside this exponential. So I put this outside. So we are left with cosine square theta plus I to I delta phi 2, which is the difference of these two phases, times sine squared theta. V is the first piece, and then here we have minus 1 minus p to phi delta t 1 2 cos theta sin theta mu first, where of course delta phi 1 2 is phi 1 minus phi. So what we have here, at a certain point when this object is going to interact with matter, the wave function is given by the superposition of electron neutrino with some probability amplitude and muon neutrino with some other probability amplitude. Okay. So let's comment this on the slide. Okay, so this is our result that I reported on the slide. So if the neutrino interacts at the time t and the distance L from the emission point along with its direction of flight, then its state in this particular space-time point is given by the superposition of electron and muon neutrino with different probability amplitudes. Now, this delta phi is phi 1 minus phi 2, but we can make it more explicit in terms of the energies and the length and momenta, okay? And it turns out that in the limit where the mass of the neutrino is negligible compared to its energy, one can write this as the difference of the squared masses of the two mass eigenstates, mu1 and mu2, okay? Divided by twice the energy multiplied by the traveled length path. And so this we can call just delta m squared divided by 2e times L. So what happens if this phase is 0? Okay, so if delta phi 2 is 0, this means that also delta m squared is 0. Okay, so there is no difference in masses between these two neutrino mass eigenstates. Okay, in this case, if you look back to here, okay, this exponential becomes 1, this becomes 1, so 1 minus 1 kills completely the second term, and this is just a cosine plus sine squared, which is just 1. So overall, if delta phi 1 2 is 0, you obtain a pure electron neutrino at whatever time and length. So there is no oscillation. Okay. However, as you understand, if this phase is non-zero, and so there is a difference in masses between these two mass eigenstates, then there is a muon neutrino component in the wave function, okay, which has to be taken into account. And so there is a non-zero probability that our initial electron neutrino will fluctuate into. Okay. So this is why neutrino oscillation is only possible if the masses are different, and in particular, at least one of the two is non-zero, which is in contradiction with the standard model, as we know. Now, with few simple passages, one can also calculate the probability that the muon neutrino oscillate into electron into muon, okay? And it turns out that one obtains this expression here. So we have a sine square of this frequency here, which is again in terms of the difference of the squared masses of the two mass eigenstates. We have the traveled length and the energy in the denominator. And the amplitude of this oscillation is given by twice the sine square of twice the mixing angle. Now, one can express this delta m squared in electron volt, the length crossed in kilometers, and the energy in GeV, and then you just obtain in your formula a factor 1.27. So it is easy to calculate this probability. And the survival probability, so the probability that you still get your electron neutrino, is of course the complement of this one, the complementary probability, so it's 1 minus this probability, and so it is 1 minus this guy here. So in this simple two-flavor case, the oscillation probabilities depend on just two parameters. One is the mixing angle, theta, and the other is the difference of the square masses. Okay? If you know these two parameters, you can exactly calculate the probability of oscillation. And the oscillation is somehow depicted here in this example. So this is calculated for 1 GeV neutrinos with a delta m square of 0.002 square electron volt, and with this value of the angle. And so what happened here? Okay, so we start from a pure electron neutrino. Okay, so the electron neutrino is 1 at time 0, and the muon neutrino is 0 at time 0. Okay, then the oscillation procedure starts. Okay, so the probability to get your electron neutrino decreases up to a minimum, and simultaneously the probability to obtain a muon neutrino increases. Okay, so when this is minimum, this is now maximum. This is the place where, for instance, the travel length, using this parameter, where you would find a muon neutrino instead of electron neutrino. Okay, then the neutrino goes away, goes on in this process, and so again the probability to find a muon decreases at the minimum, and we again a total maximum probability for having the electron, etc., etc. And the amplitude of this oscillation is indeed the square sine square of 2 theta, which is this guy here. The amplitude of our oscillation. So this depends, of course, clearly on this mixing angle. Back to our atmospheric neutrinos. Okay. So once more, in this case, the neutrino cross just a few kilometers in the air and a few hundred meters in the rock, and so nothing happens. In the other case, they cross the atmosphere, but then tens and thousands of kilometers, actually 13,000 kilometers into the Earth. Okay, and here the MSW effect enhances the probability of oscillation. So this is reported here. So here you see the probability for a muon that remains muon. Okay, this is exactly the expression that we found before. So when the neutrino crosses something like 10 or 20 kilometers in the rock, nothing happens. So it maintains its original flavor. Then going deeper and deeper into the Earth, the probability to be still a muon decreases up to a minimum, where in this point, so after 200 and something kilometers, 250 kilometers, now there is not anymore muon neutrino, but the neutrino is oscillating in a different flavor. Okay. Then it continues to travel. This is a log scale, okay, in the x-axis, okay. So the probability to get the muon neutrino again increases again after minimum, etc., etc., etc. Okay. So overall, when you look now after 10 to the 4 kilometers, which is the diameter of the Earth, okay, it turns out that the probability that the neutrino has changed flavor, the original muon neutrino from the cosmic ray has changed flavor, is of the order of 50%. Yeah, 50% probability that it is not anymore a muon neutrino. And this explains why, indeed, when looking at neutrinos from the bottom, this experiment found 1 in this ratio here, and not 2. Okay. Now let's extend this formalism to the real 3-flavor neutrinos. Okay. So now, including 3 flavors, the neutrino mix is described by unitary transformation encoding the so-called PMNS matrix, Pontecorvo Macchina Cavata matrix, which is the analogous of the CKM matrix, as you can imagine already. So here we have the 3 flavor states, here we have the 3 mass states, and here we have this transformation matrix, which is unitary. Now, clearly, one can reproduce the same analogous, let's say, procedure that I did for the simple case of 2 neutrinos, for the real case of 3 neutrinos. The algebra is a bit more complicated. Okay, if you're curious, you find this in the textbook. But let me just point to the result. Okay, so we're now considering all the possibilities. The probability of surviving for an electron neutrino is given by essentially 3 contributions. Okay, where in each time you have the square of the sign of something. Okay, and this something is essentially the difference in phase for the 2 different flavors, which can be translated into the difference in the squared masses, okay, times L divided by the energy. So again, our essentially oscillation frequency is proportional to the difference of the square masses and inversely proportional to the energy of the neutrino. So low energy neutrino have more chance to oscillate than high energy neutrinos. And then the amplitude of these oscillations are now given in terms of proper combination of the squared element of this PNMS matrix. Okay, so it is a bit more complicated, but we understand that the principle is the same. Now extended to in a 3-dimensional space. So the electron neutrino survival probability depends now on 3 different difference of square masses: delta M21, delta M31, and delta M32 squared. Okay, which are given here, because now we have to take into account 3 different mass eigenstates. Not all of them are independent. Actually, only 2 of them are independent. So usually people express the delta M31 as a function of delta M21 and 32. Now, similarly to the CKM matrix, also the PMNS matrix can be expressed in terms of the 3 rotation angle, 3 mixing angle, theta 1, 2, theta 1, 3, theta 2, 3, and a complex phase. Okay, so this is exactly specular to what we are studying for the CKM matrix. Okay, but now for the lepton scale, for the lepton sector, the CKM works for the quark sector, of course. But there is a big difference, because if you remember, for the case of CKM, only the first angle, which is essentially the Cabibbo angle, is large, and the other 2 are very small. Okay, so essentially, these, as a consequence of this, the CKM matrix is a roughly diagonal matrix. So essentially, the diagonal elements are close to 1, and the other are very small. In this case, it's very different, as you can see here. Okay, so all the values are substantial, and this is because for this case, all 3 mixing angles are substantial. They are all big angles, okay? And you see here in particular the measurement from combined analysis of SNO, Cameron, Supercamicande, Manus, Tatabay, Reno, level 2 experiment altogether. So the theta 1, 2 is 35 degrees. The theta 2, 3 is even larger, 45 degrees, and theta 1, 3 is 10 degrees. So they are all 3 large, and as a consequence, this matrix is not is very far to be a diagonal matrix. It's not at all a diagonal matrix. What about now this delta complex phase that we also studied for the CKM matrix? Okay, if you remember in CKM matrix, this delta factor, which is a complex parameter, is related to the CP violation. Okay, a non-zero value of this delta parameter corresponds to a non-zero CP violation in the weak interaction. Now, this is essentially the same. Okay. So if this delta would be 0, then neutrinos and antineutrinos would oscillate from muon to electron types with the same probability. However, a non-zero value of this delta parameter would enhance the oscillation of either the neutrinos or the antineutrinos. So the probability for an electron neutrino to oscillate into muon will be different than the probability for the anti-electron neutrino to oscillate in the anti-muon neutrino, thus violating CP. Okay. So again, this delta parameter is responsible for CP violation, but in a different sector, in the leptonic sector. Okay. If you remember, the amount of CP violation in the standard model, which is only encoded up to now in the CKM matrix, is not enough to explain the large asymmetry in matter and antimatter in the universe. So people are searching for new different sources of CP asymmetries in addition to the standard model one. If this delta parameter is different than 0, then this is an additional source of CP violation that could help understanding this mystery of the matter and antimatter asymmetry in the universe. So you understand this is very important. In fact, a precise measurement of delta constitutes one of the primary goals of the present and also next generation neutrino experiments. It is crucial to measure this parameter. What is the status? Well, until 1 year ago, so April 2020, all the available results on the complex phase delta provided only a marginal indication of CP violation in the neutrino sector. Okay, so essentially all the measured values of the sine theta, sine delta were consistent with 0 within preceding. Okay. However, in April 2020, so 1 year ago, new results from the K2k experiment that we shall discuss in a moment provide now, for the first time, significant evidence for CP violation in the lepton sector. So, significant evidence that this factor is non-zero. Okay, it is not yet at the discovery level, it's not yet 5 sigma, but it is a very strong indication, as we will see in a moment. Ok, possiamo fare una pausa, dai. Ripartiamo eventi. Domande? Dubbi, curiosità? Ok. Ok, prendiamo. Ci siete da casa? Vedete la slide?
Sì.
Ok. Okay, so we discussed about solar neutrino experiments, atmospheric neutrinos, and the formalism of the neutrino oscillation. Now, there are many other ways to study neutrinos and the neutrino oscillation phenomena. One of those is using nuclear reactors as abundant sources of neutrinos, in particular of electron antineutrinos, which come from the beta decay of the isotopes which are produced from the fission reactions. Okay, you have your scories in your reactor which decay beta, and so they produce a huge flux of neutrinos. Okay, so you can use this as a source for fundamental physics. And these anti-electron neutrinos have an energy of a few MeV, okay, and can be detected by exploiting the inverse beta decay. So an antineutrino interacts with the proton, and at the end you get a neutron, okay, and a positon. Now, reactor experiment plays at distance of the order of few kilometers from the reactor, are sensitive mainly to the θ13 angle, mixing angle. And experiments which are placed at a distance of the order of hundreds of kilometers, so far away from the reactor, are more sensitive to the θ12. Okay. Now, let's assume that the anti-electron neutrino behave in the same way as the electron neutrino, so that there is no CP violation or very negligible CP violation. Then the result of the reactor neutrino can be combined with those from the solar neutrino experiment. Okay, so we are studying essentially the same thing, but from two different completely point of view. Now, this has been done by the Camland experiment in Japan. As you see here, the structure of the detector, which is very similar to Borexino, as you can see already. So there is a huge vessel of liquid scintillator of 1 ton, and then we have all the photomultipliers. So the Camland experiment was based on use of 1,000 tons of liquid scintillator and was placed at a distance of the order of 100 kilometers from several nuclear reactors in Japan. And a clear oscillation pattern, as you can see here, has been observed. Now, these people, there was a global analysis trying to put together the results from nuclear reactor and solar neutrino experiment. Okay, see if they match together. And in this plot, you see the delta square 2,1 versus sine square θ12. So this triangle with these two blobs is the solar neutrino experiment with 1 sigma and 2 sigma uncertainty, and the star is the Camland experiment, so the reactor experiment, again with 1 sigma and 2 sigma. So if you project these two results on the horizontal axis, you see that the two are indeed very, very close. So they provide essentially the same value or very close values of the θ12. If you project on the other axis, you see that actually they provide some slightly different values for the delta n. Now, there is one way to make more controlled studies, okay, about neutrinos by producing neutrino beams with accelerators, okay, as I was mentioned at the beginning. So the results from atmospheric neutrino experiment and reactor experiment can be tested in accelerator experiment by building intense and collimated muon neutrino or muon antineutrino beams, okay, which arise from the secondary decay of pions. So you can produce pions in the primary collision, the primary decay muon, and muon provide a muon and muon neutrino. Okay, so you get your neutrinos. And then you can place your detector either close to the source of the beam, so order of 100 meters or 1 kilometer, or and actually far away, order of hundreds of tens of thousands of kilometers. Okay. Of course, the advantage is that in the accelerator experiment, the oscillation distance L is very precise measurement because you have a lab which is there and a detector which is there, also for the reactor, of course. Now, a very interesting accelerator experiment is the K2k experiment, so K2k experiment in Japan. And this was the first accelerator-based neutrino experiment. So here we have the K2k laboratory in Japan, where they provide this beam of neutrinos. And then they put two detectors. One here, the near detector, okay, only 300 meters from the source. And the other at a distance of 250 kilometers. Okay, so the first detector is close, so they interact indirectly. In the second detector, the neutrino have to pass through some layer of Earth before interacting with the detector. Okay, and so as we studied, crossing matter enhances the oscillation probability. Okay, and in fact, the K2k observed a total of 112 events against the expectation of 160 events. Okay, the expectation in case of no oscillation. So again, it is another proof of neutrino oscillation through matter. Now, let me show you a view of the Super Kamiokande. So the Super Kamiokande is this impressive tank of 50,000 tons of ultra pure water. This is underground in a mine in Japan. You see here also the dimensions, so it's 40 meters times 40 meters. And all this ultra pure water, where the Cherenkov effect is exploited, is surrounded by, you see here, a wall of 11,000 photomultipliers. This is a nice picture during maintenance. So there's a little boat with the two technicians who are repairing some photomultiplier in this nice swimming pool. Now, the K2k was the first generation of this experiment. The second generation is the T2k that I was mentioning before, so Tokai 2 Kamioka. This was now located at 295 kilometers from the accelerator, and the near detector at 280 meters. Okay, so in this case, the muon neutrino beam had an energy of 600 MeV and an intensity which was 2 orders of magnitude larger than K2k. Okay, so a lot more intense neutrino beam. And the T2k detector, which is still based on the Super Kamiokande long distance detector, detected for the first time the appearance of electron neutrino starting from muon neutrino. Okay, so this is not anymore a disappearance experiment as the solar neutrino, but for the first time an appearance experiment. Okay, so something that the result of the oscillation is not detected, appearing in the detector. You start from a pure muon neutrino, you get some rare electron neutrinos. As a neutrino beam travels through Earth, of course, a fraction of the muon neutrino and muon antineutrino oscillate into either electron neutrino and electron antineutrino. Okay, and these are recorded by the Super Kamiokande, where once these neutrino interact with the atoms of the ultra pure water, the weak interaction, they convert into the charged electron, and the charged electron then produces the Cherenkov effect in the water. Okay. So you have your incoming electron neutrino. It interacts with some atomic electron in the water, producing now the electron. The electron moves faster than the light in water, and so produces a Cherenkov light in a cone, which is now projected as a ring in the photomultiplier layer. So just to give you some picture, Super Kamiokande was able actually to distinguish between Cherenkov rings produced by muons and by electrons. The origin of this difference is because the two have very different mass, and this of course has an impact also in the Cherenkov light distribution. And in particular, it was found that the rings originated by muons were very cleanly defined, and the rings originated by electrons were much more confused. Okay, so the light was much more diffused around the ring. So there was a clear way to distinguish between a muon and an electron. And also you see here rings created by electrons originating from the electron neutrino with some nucleus, or with positrons, okay, originating from the antineutrino. And this is relevant because so people were also able to distinguish between those two, and this is relevant for what we will know in a moment. So as I was anticipating, in April 2020, so 1 year ago, the K2k experiment reported the strongest evidence so far that CP symmetry is violated by the weak interaction of leptons. Okay? And more specifically, based on an analysis of 9 years of neutrino oscillation data, the K2k result indicate a 3 sigma level discrepancy between the probability that the muon neutrino oscillated into an electron neutrino and the CP counterpart, so the probability that the muon antineutrino oscillate into the electron antineutrino. Okay, so they found a mismatch, okay, discrepancy, and a rather large one. Okay, so in this plot here, which is the result, you see the sine square theta to 3 on one axis, and most importantly, the delta complex parameter of the PNMS matrix, okay? And as you can see, the data sits here, and this is a 3 sigma level discrepancy with respect to the 0 value, okay? So for no CP violation, you expect your result somewhere here, but it is there. And so there is a 3 sigma tension with respect to the non-CP violation hypothesis. And this is the strongest evidence so far of CP possible CP violation in the leptonic sector, okay? So these results were published on Nature, of course, last year, on 15th of April. Constraint on the matter-antimatter symmetry violating phase in neutrino oscillation. This is the title of the paper. Now, this is a 3 sigma level, so it is a strong evidence, but not yet a discovery. So while further data are required to confirm these findings, the results offer hope for future discovery of leptonic CP violation at K2k or at next generation neutrino experiments. Another interesting accelerator experiment is the one, again, that involves the Gran Sasso laboratories. Okay, this is the OPERA experiment. So that was operating in the past years. So a 17 GeV muon neutrino beam was produced at CERN from the SPS machine, and then the neutrino traveled through Earth all the way to the Gran Sasso laboratories, so crossing a distance of 700 kilometers underground. Okay? And then they interact with, in a very few cases, with the detector. The detector was a very sophisticated one. It used 1,200 tons sandwich of photographic emulsion films with lead plates. And it was needed in order to detect the tau lepton, because people were searching for the oscillation of the muon neutrino into the tau neutrino. So at the end, you have to detect a tau lepton. So it was, again, an appearance experiment aiming at detecting the neutrino tau starting from a pure beam of muon neutrino. This is an example of the result event and also the detector. The detector is a layer of lead, okay, sandwiched with these photographic emulsions. And this kind of setup allowed to reach extremely high spatial resolutions, order of microns. So what happened is that when this happened, very rarely, that a tau neutrino, so the muon neutrino oscillates into a tau neutrino through the way from CERN to Gran Sasso. Then the tau neutrino somehow interact with matter, okay, with the lead in particular, lead nuclei, and it converts into a tau, okay? In the reaction, also some hadrons are produced, which can be traced in the detector, and then the tau lepton, which is a very heavy and unstable object, decays quite soon into some final state. For instance, so here we see a muon and then 2 neutrinos, we don't signal in the detector, okay? So at the end, people was able to reconstruct this very, very rare event, which were the proof of the oscillation of the muon neutrino and the tau neutrino. So OPERA conducted data taking in 2015 and reported in total five tau neutrino events. But this was enough because considering the essentially zero background, this was already above the threshold of 5 sigma. Okay. And then the data were also reanalyzed in the following years. In 2018, they found another 5 events. So in total, 10 events. Okay. Now, as we've seen, the neutrino oscillation probability does not directly depend on the mass of the neutrino, but rather on the difference of the squared masses. Okay. So by measuring the mixing angles, for instance, you are sensitive not to the mass of the neutrinos, to the mass of the mass eigenstate neutrinos, but rather to this delta n squared. And so indeed, experiments are only sensitive up to now to the squared mass differences, but not to the absolute values of the neutrino masses. Now, one can, of course, perform a global analysis of all the data available now from reactor experiments, accelerator experiments, cosmic neutrino, whatever you want. And today we have a rather precise measurement of this delta m squared. Okay, so it turns out that delta m squared 2-1, so between the first two mass eigenstates, is very, very tiny, 7 10 to the minus 5 squared electron volt. Whereas delta m32 is significantly larger, 10 to the minus 3. Okay, so there is almost 2 orders of magnitude here. Now, regardless of the absolute mass of the lightest neutrino, which we don't know at the moment, there are two possible hierarchies here. So the so-called normal hierarchy, where the M3 is heavier than the 2, which is heavier than 1, which is reported here. Okay, so these are the three masses of the three mass eigenstate, M1 and M3, or the inverted hierarchy, okay, where M3 is the lightest, and then we have the other two here. Okay. The only thing we know is the difference between 1 and 2 and 2 and 3, but we don't know which of the two hierarchies is the right one. So in other words, the current experiments are not sensitive enough to discriminate between these two possible scenarios. Okay? And of course, this is the task for the new and future generation of the neutrino experiments. What we can say about the absolute value of the neutrinos? So although they are not known, it is clear that they are very small. Okay, and this is also the reason why they cannot be accounted in the Higgs mechanism. So the present delta m square measurement suggests the mass of the neutrino in the range between 1 and 100 milli electron volt, so below 1 electron volt, with a lower limit of 60 milli electron volt for the sum of the three masses. But we have also other different constraints. So from study of the endpoint energy of the electron in the beta decay of tritium, it is known that the mass of the lattice neutrino must be smaller than 2 electron volt. And we also constraints from the cosmological data. Okay, the universe is completely filled by neutrinos, so they are extremely light, but there are so many. Okay, that for sure they also have an impact in the possible impact in the evolution itself of the universe. So neutrino contribute to the energy density of the universe, playing a role, the role of so-called hot dark matter that we study tomorrow. This means relativistic light particles that don't emit light. And so one can combine our results, also including data from the cosmic background radiation, etc. And at the end, so the constraints from the cosmological prediction is that the sum of the mass has to be smaller than 1 electron volt. Sorry. Okay. So we don't know yet the absolute values. We know that they have to be very, very small, fractions of electron volt. Okay. Since we still have 20 minutes, let me continue just 10 minutes, no more than that. Let me just make a summary, okay, of what we have learned so far in this course. Okay. And this will bring us to more from what is outside, okay, what is beyond what we've learned, okay, so this is beyond. So let me just summarize what we know and what we've learned about the standard model. So the standard model is the modern quantum field theory of elementary particles and their fundamental interaction, okay. It includes a description of the unified electroweak interaction and the strong interaction, whereas the gravitational interaction, as you know, is not included. Electromagnetic interaction and weak interaction are interpreted as different aspects of one single unified interaction, which is the electroweak. And in fact, as we've seen, their charges are connected by through the Weinberg mixing angle, G, E, G prime. The Lagrangian, the overall Lagrangian of the standard model is the sum of the electroweak Lagrangian, including the Higgs sector, plus the QCD Lagrangian, the SU3 Lagrangian that we study as a separate argument. Of course, the standard model is everything go together. Okay. And so at the end, the standard model Lagrangian has to be symmetric under the global gauge transformation of this group, okay, which is now the combination of SU3 color and SU2 left U1 charge. Okay. So it's not just this plus this, but it is altogether the symmetry group of the standard model Lagrange. Okay. Now, gluons carry color charge, as we know, actually charge and anti-charge, color and anticolor, and can therefore interact among themselves, generating 3 gluons and 4 gluon vertices. Similarly, also the weak bosons carry weak charge, which is the third component of the weak isospin, which is zero, and thus they can interact among themselves. For instance, we know that we have ZWW vertices, okay? And these actually, the vertices are necessary to solve the problem of the unitarity violation of the cross-section, if you remember, okay? Now, it is a consequence of the fact that both SU3 core and SU2 left are non-abelian group. Okay, so they allow for set interaction of the gauge fields. The standard model exhibits also additional symmetries, which are collectively known as accidental asymmetries, which are not gauge symmetries. And are continuous U1 symmetries of the standard model Lagrangian. And by another theorem, we know that each of these accidental symmetries has to be associated with some conservation law. And this is indeed the case for electric charge, baryonic number, lepton flavor number, etc. All these are so-called accidental asymmetries of the standard model. They do not arise as gauge transformation, but as continuous U1 transformations. Different conservation law apply to the different interaction. As we know, all three interactions conserve energy, momentum, angular momentum, charge, baryonic number, and electronic number. But the quantum numbers which determine the quark flavor, so the isospin, third component of isospin, strangeness, charm, beauty, and truth, are only conserved by the strong and the electromagnetic interaction, but are not conserved by the weak interaction as well. And the magnitude of the strong isospin is only conserved by the strong interaction. What about now parity and charge conjugation? They are conserved in strong and electromagnetic interaction, but not in weak interaction. In particular, we know that the charge at current weak interaction result in a maximal parity violation, in the sense that they can only couple with left-handed fermions and right-handed antifermions, and not vice versa. And parity is also violated in the neutral current weak interaction, but not maximally, okay? Because neutral currents can interact both with left-handed fermions and right-handed fermions, although they do with different couplings, with different strengths, as we studied. And the CP is also violated in weak interaction, as we studied also. What about CP violation in the strong interaction? This we never discussed. So the QCD Lagrangian could, in principle, also have a CP violating term. However, the experimental results are consistent with the null CP violation, so or something which has to be smaller than 10 to the 10 to the minus 10. So to the present knowledge, there is no CP violation in the strong sector, only the weak sector. What about neutrinos, as we studied today? So in the original version of the standard model, all neutrinos are massless. They don't interact with the Higgs field. And so the observation of the neutrino oscillation, however, implies that neutrinos have to be massive, okay? At least two of them. This brings to electron mixing, which is analogous to the quark mixing, okay? And electron mixing is described by the PMNS matrix, which is the analogous of the CKM matrix that we already studied before for the quark sector. And the PMNS matrix, which accounts now for the essentially for the mixing of the electron sector, so for the neutrino oscillation, has now more recently been incorporated in the standard model. Okay, so it was originally not there, but now we know that it has to be there because neutrino oscillate, so they have to have mass, and so the standard model has, let's say, minimally extended also to include the mixing in the electronic sector. In the standard model, as we've seen, the particle masses, with the exception of neutrinos, are generated by the Higgs mechanism, which is, of course, an essential ingredient of the theory. And after spontaneous symmetry breaking, the symmetry group of the electroweak sector, which is Lu2 left times U1 hypercharge, reduced to the simple electromagnetic gauge group. And the U1 electromagnetic and SU3 core symmetry remains instead unbroken. So the Higgs mechanism breaks the electroweak gauge group, gauge symmetry, spontaneously. What is the implication of this? Now, a renormalizable gauge theory of weak interaction is only possible in conjunction with the electromagnetic interaction in the framework of the electroweak unification. So only a theory which is based on the SU2L U1Y is renormalizable. Renormalizing means that we don't have infinities when we account for higher order terms in the expansion in the coupling constant. and it is a necessary requisite for a physical theory, okay? For a physical gauge theory. So, again, a renormalizable gauge theory of the weak interaction is only possible in conjunction with the electroweak, okay? This unified gauge theory works, however, only at energies above the spontaneous symmetry breaking, so above essentially the scale of the electroweak bosons, above 100 GeV. Okay, so when you go down below this energy, the electroweak gauge group is broken spontaneously, and we don't have anymore a gauge theory for the weak interaction itself. So what about the V-A theory that we discussed quite a lot? The V-A theory allows the description of an enormous amount of experimental data, but it is, however, only a phenomenological theory, since it is not renormalizable. Okay? So a renormalizable theory of weak interaction has only to be in conjunction with electromagnetic interaction and above the electroweak scale, so above 100 GeV. When you are below, the symmetry is spontaneously broken, and we only have in hand a phenomenological theory for the weak interaction, which is the V-A. This means that the contribution of higher order terms in the perturbation expansion in the weak coupling constant, which should be negligible in a normalized theory, are not negligible, and they diverge at a certain point. Okay. Now, the standard model has received very strong experimental confirmations in the case of experiments, different energies, different setup, different criteria. Everywhere you touch the standard model, it essentially works. Okay. And of course, the recent discovery of the Higgs boson constitutes the final proof of the theory. Now, however, as you already know, despite the astonishingly high level of agreement between standard model prediction and experimental results, the standard model cannot be considered the ultimate theory of particle physics. And there are many reasons for that. First of all, is that it requires 25 free parameters. So this cannot be a fundamental theory. We have to put by hand, so by experiment, the value of these 25 parameters. So what are these parameters? These are the 12 masses of the elementary fermions, quarks and leptons, the 3 coupling constants, so for instance, alpha electromagnetic, weak and strong, or if you like, the charges, the strong, weak, and electromagnetic. 2 parameters for the Higgs potential, the mu and the lambda, or alternatively, the vacuum expectation value and the mass of the Higgs, which are all interconnected. 4 parameters for the CKM matrix, and 4 parameters also for the PMNS matrix, okay, so the mixing angles in the electronic sector. So overall, there are 25 parameters which are needed for the theory to work, but which cannot be predicted. So those values cannot be predicted by the theory itself, starting from first principles. But this is not the only reason. So the large number of free parameters and the impossibility to include gravity actually are not the only reasons to consider the standard model unsatisfactory. Okay? The standard model, in fact, leaves several fundamental questions unanswered. So first of all, why there exist 3 families of quarks and leptons? Why not just one? So ordinary matter is made by protons, so up and down quark, electrons, and neutrinos. So why do we need the second and the third generation of quarks and leptons? We don't know, and the answer is not provided by the standard model itself. Why the particles have so different masses? So the mass of the neutrino being a fraction of the electron volt, and then the top quark is 200 GeV. Okay, what the hell? But also, what determines the magnitude of the coupling constant of the different interaction? Are the strong and the electroweak interaction also different aspects of a single, unified, more general interaction? What is the origin of CP violation? What happened to the primordial antimatter in the universe? So these are all questions that do not find an answer within the standard model. And there are even another more fundamental problem, which is about dark energy and dark matter, as you know very well. Okay. So dark energy is attributed to a non-zero cosmological constant in the Einstein equation of general relativity, and essentially this tends to accelerate the expansion of the universe starting from 5 billion years after the Big Bang. Okay. But what is dark energy? We have no idea, and we cannot find an answer within the standard model. Okay. What we know from cosmological constraints and experimental data, observational data, is that it constitutes almost 72–73% of the full universe energy content. And what is dark matter? This we either don't know. Dark matter accounts for something like 23% of the universe. So what we really know, what we really can describe with our standard model, is only 5% of the content of the universe. All the rest we don't know and is not provided by the standard model. Okay. So there are plenty of reasons to consider the standard model not the ultimate theory of elementary particles and fundamental interaction, but rather just a model, although, as you can imagine, a very sophisticated and elegant model. I'm always impressed when I teach the Higgs mechanics. It's really something incredible to me, and how it actually really works. And all this works extremely well at energy up to the electroweak scale, so above 100 GeV, essentially. Now, since decades, theoreticians have been working hard to develop new and more general theories, okay, that include the standard model as, let's say, low energy limit or low energy approximation. And this is, of course, a quite challenging job. Now, some of these theories, such as the supersymmetry that we'll discuss tomorrow, work at a relatively low energy scale, so the scale of the TeV, which is at which now the Large Hadron Collider in principle, or at close future accelerators. But others, such as the grand unified theories of supergravity, work at much, much higher scales, so 10 to the 16 GeV or 10 to the 19 GeV, which you can never reach in a laboratory, in an accelerator on Earth. Okay. Now, since these energies are well beyond the reach of the present and future accelerator on Earth, the only possibility to test these more general theories is to search for relic particles produced in the very, very first moment of the universe, where the conditions of temperature and density were extremely high. Okay? Such as searching for magnetic monopoles, also this we will discuss tomorrow, or searching for a very rare phenomena such as the proton decay that we mentioned in the past, and we will also discuss tomorrow. Okay. So that's it for today. So we have a beautiful theory, which is not actually a finite theory. Final theory is a fantastic model, but which needs to be implemented and extended. Okay. Okay. So see you tomorrow online, so 100% on remote at 3 p.m. Okay, see the last lesson.